So these are the photo sensors I got, driven by 5 volts. There's an LED on one side and a sensor in the other that just lets the 5 volts out. So one side's got a 50 ohm resistor for the LED, because they take about 68 milliamps, which is quite a lot, but there we go. Seems happy enough with it. And the other side I've put on a 200k. So the idea is that those are both grounded, and then I will put my sensor from the Arduino onto the output of there, but before the 200k resistor, and then when that goes on, 5 volts appears here, and my Arduino will trip. So I've got 2 of those, wherever the other one's gone. There it is. And on my motor, I've put the rotor there, and I discovered that it had these 2 nice handy little notches out of it, which are 180 degrees from each other, exactly across the pace there. I got the 3D printer out in Fusion 360, modelled this up to use it as a cutting tool, and then made these, which will hold the photo sensor in this part, let the wires out the back, and then in there is a little notch which goes into the side of here, and one of them is in the dead centre, which is that one, and then this other one is offset by the 90 degrees required. Well, it's not 90 degrees of this, it's 90 degrees of one of these slats. So I can't remember exactly what it ended up. And then those will mount on there, hold my photo sensors in place, and we should get some quadrature readings. And I've got the 2 encoders here, which they are offset from each other relative to one of this blanked in parts of here by 90 degrees. So it worked out, I think it was 5.7 degrees or something, to get the right offset between the 2 of them. And the idea is that when you drive the motor in one direction, one of them will trip first, and when you do it in the other direction, the other one will trip first. So you can tell, you can just count the ticks to get your speed and distance and what have you, but when you add the second one, you've also got direction. So I've hooked it up to the power supply and the scope here, and we'll see it in action. So currently they're both off, and when we give it some juice, you can see that the waveform there, it's triggering on the yellow, the first channel, and if you read the blue channel at the time when it triggers, it will be low, because the blue channel is trailing the other channel by 90 degrees. And I'll just quickly change things around. Right, so it's just a DC motor, so we'll just swap the contacts over. And now, when I give it some juice, you can see that it's triggering on the yellow still, but if you read the blue channel at the trigger point of the yellow, then it's on. So that means it's spinning in the opposite direction. I printed this out to demonstrate the quadrature a bit better. It didn't come out terribly great, but it's good enough for this. So basically this is quadrature at its most simplest. So if you have a wheel that is 180 degrees blanked and 180 degrees not, then you put a sensor in a position, then only ever trigger it on the rising edge, so when it goes to the blank bit, you'll get 1 tick per turn, and you'll know that that's how fast you're going. If you add a second sensor at about 45 degrees, which is quadrature, it says 90 degrees because there's 360 divided by 4 is 90, but it's 90 degrees of the blanked out section. So 90 degrees, a quarter of 180 is 45, so if you imagine that's at about there. And then if this is spinning, then when it gets to that position and triggers on this rising edge, then this one obviously is blanked out, so it will read high or low depending on what you're doing. If it's going the other way around and it triggers on the rising edge, and this is here at 45 degrees, you can see it's quite clearly in the blank area, so it will be the opposite, and therefore you know when this one triggers on a rising edge, you read this one and you know which way it was spinning, and that's quadrature.